Hi, my name is Oliver Maher, and I'm a senior at Clayton High School, which is in St. Louis, Missouri. Today, I'm presenting for the Winter International Young Researchers Conference on my project about naturalistic monitoring of locomotion, which reveals step speed deficits in SOD1 ALS mice. So, let's first talk about some background. What is ALS? ALS, also commonly known as Lou Gehrig's disease or amyotrophic lateral sclerosis, is a devastating motor neuron disease. So what it does is it degenerates the connection between the motor neuron and the muscle, as we see in this first diagram. And what that causes is motor decline. So early stages of ALS can be more smaller interactions. So it can be stuff like buttoning up clothes, maybe typing on a keyboard, you type a little bit slower. But that eventually and very quickly becomes middle stage ALS, where muscles become paralyzed. And what this causes is it's a lot more strenuous to walk. Many times you need a walker. Um, and you start to like lose your, what's it called? Ability to talk slowly, and just breathing becomes a little bit more difficult. But that gets much worse very quickly. So late stage ALS, completely like mobility, you just completely lose your ability to walk. People usually need devices to help breathe. Your voice changes a lot, and like you can't like throwing a ball, anything like that just becomes extremely difficult until you get to end stage ALS. Usually, about people last like 2 to 5 years before they end up dying. Usually because the chest muscles are so weak, it's difficult to breathe, and usually people die of respiratory issues. It's an extremely devastating disease, although only about 5 in 100,000 people have it, so that equates to about 30,000 in the US. Those who do have it struggle very much, and it's extremely fatal, with only 10% making it more than 10 years and 5% making it more than 20. So, the issue that the reason it's so difficult to catch is because like the brain is extremely flexible and extremely efficient. So it can optimize itself, even though like for example, even though 70% of the neurons can be gone, it can still function normally. And only after that, when more than 70% of the neurons are gone, will you actually start seeing symptoms, because the brain just, even though it's already optimized so much, it just can't optimize further. But these optimizations still come with a hidden cost. It's not that the brain becomes uh, like it still retains the same amount of efficiency as before, but instead you just, for example, prefer to take the stairs less. These little differences, and you just, instead of like walking all these different ways, you just like start walking the same way more frequently. So you can still walk as well, you just can't do as many different things, but they're extremely subtle and difficult to notice. So, the biggest issue when it comes to this ALS research is in the traditional mouse models, there's tons of experimenter bias. And there's a few reasons why experimenter bias is bad. One, there's just experimenter stress, right? So, experimenter bias is something like a Skinner box, where usually the researchers will use operant conditioning to reward the mouse when it does a certain behavior. For example, pulling a lever is an extremely common example. And pulling a lever, researchers used to prefer it because basically when you pull a lever, you're only looking at one dimension of movement. And it's a really simple task to study. But the issue is, one, it causes stress in the mouse because it's constantly doing this task for like a reward, like food that it needs. Um, but additionally, it's just less ecologically valid because this mouse is being trained for this exact same task that it does over and over and over again, which just isn't the way and the variety that like normal natural mice and natural humans have. So it's not ecologically valid and applicable to humans. Whereas the apparatus that we went for in the Hengen lab was a system where mice could cross a ladder 24/7 whenever they want, just to get between back and forth between their food and water. And they didn't have any constraints on them, they were just being monitored, and we recorded their feet. So let's get a little bit more into how the apparatus works. So on the left, we have a picture of our apparatus. This is the bridge where the mice walk back and forth. So on one side, we have food, on the other side, we have water, and in between, we have these electrode sensor rungs that record at 1000 hertz. So we have 10 rungs. Each one can tell which side was on in the exact millisecond it was touched. So for our experiment, there were 4 subjects, 2 SOD1 ALS mice. SOD1 is just a variation of ALS, the first variation in DNA that was discovered, and then 2 wild-type control mice. And we recorded them from postnatal day 60 to about postnatal day 160, but usually they didn't last that long. And in total, this apparatus yielded 110,000 crossings analyzed. So, what do we do with all of this data? So, initially, what happened is when I came into the lab, I received this data as packages of just every single touch in each cross. I received the basically beginning of the touch, the end of the touch, and which rung for all of the touches in one cross over the ladder. And then with the assistance of the PhDs that worked with me, like Jimmy Zong, we quickly, easily developed algorithms that filter out incomplete crosses. So, for example, when a mouse crosses halfway or when it doesn't, and misfires that when the data messed up. So we quickly eliminated all of those incomplete crosses, or the mouse touches are wrong, or its tail touches, stuff like that. But next we need to classify meaningful crosses, because we don't just want every single cross, because sometimes it might be playing around and it might just be touching a tons of rungs around it, which makes it difficult to determine the actual measures. So using machine learning, and about I think over 1,000 hand-labeled frames, so because we also had a video recording in our apparatus, we were able to compare the video recording, determine that the mouse was not doing a quote purposeful cross, which we only wanted purposeful crosses, and using machine learning, we said, hey, during this cross, the mouse was playful, watch its rung ladder data and identify connections. So we got the machine learning model to an extremely high accuracy rate, and then applied it to all the data, so we only had the purposeful crosses. From there, I calculated the kinematic measures and tested a bunch of different kinematic measures, from simple stuff to step length, stride duration, and stance duration. Stride and stance and step are just all different components of gait, measuring which kinds of gait, the asymmetry indices, step lengths, and more, and then basically ratios of these different variables. And from there, I basically had the trial day when it occurred on, and the actual measure. So the speed, stride duration, stance duration, and step length, what's it called, asymmetry or whatever. And from there, first thing I did was use a piecewise linear regression model to basically identify, because obviously these symptoms take time to develop, right? And it's not like the passage is born and then immediately extremely noticeable effects of ALS are going on. So first there's the learning phase, because this ladder, right, we didn't teach it how to work the ladder like an operant conditioning type, but obviously walking across ladder is less natural. So they both have their learning periods. But then once that learning period ends, I used a piecewise linear regression to separate just once the learning ends, how does the performance look? And then I used bootstrap slope estimates, which is just this is just more computational math and statistics to basically get the slope of the post-learning trajectories of the mice and compare them statistically to see if there's a statistically significant difference and how significant that difference is for these kinematic variables. So the most significant finding was a progressive decline in ALS mice and wild-type mice in the step speed. So we can see this graph here clarifies a lot. For starters, things I should clarify, trial day, when day 0 is actually postnatal day 60, so it's day 0 of the experiment, but they're already at 60 days old. So, the speed, and we can see that, the wild-type mice, it looks like it basically finishes its learning a little bit quicker, also sort of consistent with the mouse, basically, if it's less impaired, it can learn more quickly, but after that, you can see that it declines. The wild-type mice stays flat, and the ALS mice declines. You can see that in both the standard deviations, but additionally, you can also see that in just the slopes. And if we look at the actual numbers, the wild-type increases by 0.0015 centimeters per second per day, so just barely increasing. Honestly, that's negligible compared to the ALS mice, which decreases by 0.1 centimeters per second per day, so meaning over a week, it almost loses a centimeter per second in its walk. Additionally, we can see the other variables that changed were the stride duration and stance duration both increased. So basically just overall, each stride it took was longer, and the amount of time its foot spent on the ground, that's what stance duration is, the component of your gait where your foot's on the ground, increased, and the step length typically decreased. But you can see, although here the ALS mice, in this case it's inverted, right? So that you want the stride duration to basically you want the stride duration to like increase, but generally speaking, what happened is like there's a lot less variation, and that's important, and we'll talk about that a lot when we come to these naturalistic models. So essentially, um, to summarize, right, step speed is the most sensitive indicator of ALS motor decline, and we saw in the graph that it's really clear. But the biggest like controversy around these naturalistic models is they're a lot more difficult to determine because there's just so much randomness that goes on. It's not just a simple task like pulling down a lever, which is extremely rigid but also simple every single time it's done. These naturalistic movements, sometimes the mouse might just move slower that day. Sometimes it might be really playful. Sometimes, I don't know, it's breakfast, like I don't know, it enjoyed its breakfast more and it was like running around and being a lot faster. So there's just so much more variation in this data. But that variation is a good and bad thing because while honestly the variation makes it a lot more difficult to study, it also shows that even if there's this variation that goes through and the mouse isn't being trained to do the best it can at this task, this um, the kinematic measures still show a clear significant difference in the steps between ALS mice and wild type mice in its completely natural random behavior. So the future study for this plan would be one, to just increase the study because two per group, although it yielded tons of crosses, just a very small number. But on top, so we want to get one more mice, but additionally, we want to get more. We want to add head stages to the mice to track the neural activity and see how the neural activity coincides with the actual neural generation. I'd like to give a huge thank you to Dr. Rovi Chopra for his mentorship. This project wouldn't be possible without him. Jimmy Zong for all his help with the programming, and Dr. Keith Hengen for his lab resources. Thank you so much.